Okay, guys, it's going to connect in a second or so.
Okay. Yeah, it's on. I can see it's streaming now, Jerry.
Okay.
Okay.
Wait, just
Streaming now.
okay, I'll start now. Hello and welcome to another edition of the NSF Wednesday Colloquium. This is Jyotishman Dasgupta, and it's indeed my pleasure to welcome. It is indeed my pleasure. It's indeed my pleasure to welcome Professor David Neufeld from the Johns Hopkins University for his NSF Wednesday Colloquium today on the 23rd of September. Actually, the Wednesday Colloquium is historically the oldest scientific forum for the Tata Institute of Fundamental Research in Mumbai. It actually started at the time of Homi Bhabha, when he was still directing this institute. And it has always been a playground for discussion of science at the highest level within the physicists, the chemists, and the biologists. So it's pretty important in a traditional part of TIFR. And I really welcome David to give his colloquium today as part of this series. I have my colleague, Professor Manoj Purvankara, who is going to introduce Professor David Neufeld formally. So I hand over the reins to Manoj. Manoj?
Can you hear me, Jyotishman? Can you hear me?
Yes, we can hear you.
Okay. Yep. Thanks, Jyotishman. Friends, it's a pleasure to have Professor David Neufeld as our colloquium speaker today. David is currently a professor in the Department of Physics and Astronomy of the Johns Hopkins University, USA. David obtained his PhD degree from Harvard University in 1987. He then spent close to 3 years as a postdoctoral fellow at the University of California, Berkeley. In 1989, he joined the Department of Astronomy and Astrophysics at the Johns Hopkins University as a faculty and has been there ever since. As I said earlier, he is currently a professor there. David's primary research interests are in molecular astrophysics, and interstellar medium, astrophysical masers, and infrared and submillimeter astronomy. David has co-authored close to 400 research articles on these topics, with over 100 of them as the first author. He has a total citations close to 15,000 and has an H index of 67. On a personal note, I have worked with David on and off for the last decade or so. It has been a wonderful experience working with him, and I must say that I have learned a lot from him. In this colloquium today, David will give us an overview of the molecular universe and tell us how studies of molecular ions can be used to determine the density of cosmic rays in our galaxy. Please join me in welcoming Professor David Neufeld to giving this colloquium. David, the floor is all yours.
Thank you very much, Manoj, and thank you for the very nice introduction. So it's a real pleasure to be able to speak to you in these difficult and strange times. And I'd like to start just by hoping that everybody who's listening is staying healthy and keeping safe. So what I wanted to tell you about today is the molecular universe. And let me start just by saying that molecules have been present in the universe since the very earliest times. In fact, the first molecule, we believe, formed less than 100,000 years after the Big Bang. This is all according to theoretical models. And it was, astronomers think, a particular molecule, a rather unusual molecule, the helium hydride cation, HEH+. So as you probably know, we have this picture that the universe started in a big bang, very hot, and it would have been completely ionized to start with. But then as time progressed, the universe cooled and ions recombined to form atoms. And that's shown in this plot here, which shows you the composition of the universe as a function of time moving to the right, or redshift moving to the left. And the first atom to form was helium. And at that time, the universe was still, or the hydrogen was still fully ionized, and the helium could react with the hydrogen ions to make this simple molecule with 2 electrons and 2 nuclei. So this is really a dramatic indication, according to these models, of the universe's tendency to form molecules very, very early on, before there were any stars. I'll just say as an aside that this molecule, HEH+, has been detected very recently in the nearby universe. So not at the early times when it first formed, but actually in a nebula surrounding a very hot star. And this detection was obtained using NASA's airborne observatory, which is called SOFIA. This is the Stratospheric Observatory for Infrared Astronomy, operated jointly by NASA and the German space agency DLR. Well, molecules are now ubiquitous in the universe, and we observe them in a great diversity of astronomical environments, in stellar atmospheres, in envelopes that surround stars that may be losing their atmospheres, in the atmospheres of planets, both in our solar system and planets orbiting other stars, in comets, in the disks that surround young stars in the process of formation, and also the disks that are present at the centers of active galaxies where a supermassive black hole is accreting material. And finally, and this is the case I'll focus on today, in interstellar gas clouds in our own galaxy, the Milky Way, and in other galaxies as well. So my plan for today's colloquium is, first of all, to tell you about the interstellar medium, that is the gas that pervades our galaxy in between the stars, and the molecules that are found there. I'll then talk about a different constituent of our galaxy, the cosmic rays, which are highly energetic and often highly relativistic charged particles, electrons and nuclei. And then I'll discuss how, through careful interpretation of observations of molecules in the interstellar gas, we can essentially remote sense cosmic rays and determine their density throughout the galaxy. Okay. So let me start with the first part of the talk and say a few words about the interstellar medium. So galaxies have much more in them than just stars. They're filled with a tenuous interstellar medium composed of atoms, molecules, and small, by which I mean submicron solid particles, silicaceous and carbonaceous in nature, which astronomers call dust grains. And the typical particle density is extraordinarily low by the standards of a terrestrial laboratory, with particle densities between about 0.01 and 10 to the 4 particles per cubic centimeter, and temperatures that cover a huge range from about 10 Kelvin to 1,000,000 Kelvin. And this gas is composed of the elements we all know of, but 90% of the gas is hydrogen, about 10% by number is helium, and all the other elements constitute only about 0.1% by number. And these elements were all made in, with the exception of lithium, were all made in stars by the nuclear reactions that power the stars. And astronomers, for reasons that will sort of astonish chemists, call all of these metals. So oxygen, nitrogen to astronomers are called metals. And
Can I ask a question? Can I ask a question, David? This is Jyotishman. How does one quantify these numbers? In a sense, how do you measure these typically? There must be spectra available for these,
yes.
Yeah.
So basically, through a careful analysis of the spectra of stars, and particularly the sun, of course, where we have essentially infinite signal to noise ratio in our observations, we can determine the abundances. Another thing we can do in the solar system is gather material, say from meteorites, which have abundances that by and large reflect those of the sun. And there we can actually study them by mass spectroscopy.
Okay, so this is just because purely based on, since some of us are chemists here. So
yeah.
There could be elements that are dark to these spectral tools, right? So would you miss certain elements
Well, I think in the sun, almost all of the elements have been detected because one has, such a bright source, one can get a spectrum of exceedingly high signal to noise ratio and see very, very weak features. But in other stars, indeed, the less abundant elements will escape detection. So this interstellar gas is, in fact, divided into many or several different phases. And material is sort of moving from one phase to the other and between the interstellar gas and stars. So I've sort of represented this by the diagram shown on this slide. So one might start with stars, and they can lose mass, particularly in the later stages of their evolution, when they become giant stars and the gravity of the surface of the star is diminished. And so they can release gas into the interstellar environment. In the case of massive stars, and by this I mean stars that start their life with about 8 times the mass of our sun or larger, they'll end their life very dramatically in a supernova explosion. And that will release, in fact, the majority of the material that made up that star into the interstellar gas. And these supernovae can heat up the interstellar gas. And so one has a phase of very hot ionized gas. Then one has gas at around 10 to the 4 Kelvin, not quite as hot, that is ionized by stars, a plasma. And then this gas can collapse and form cold clouds that are mainly neutral, mainly consisting of hydrogen atoms, and they're much cooler. They're at about 100 Kelvin. And then if they collapse under their own weight to form denser clouds, those clouds can become molecular at their center. And there the temperature would only be about 10 Kelvin. And then these molecular clouds, and you'll see them in this previous slide, these dark so-called pillars of creation are dark because they're quite dense and the light is being absorbed by the small solid particles. But these are the sites of star formation. And so there's sort of a cycle that goes on where material goes through the interstellar medium, and then through a star and then back into the interstellar medium, polluted with the heavier elements, astronomers' metals. And so the interstellar gas gets enriched as time goes on with these heavier elements, of course, the elements out of which we are made. There's a transition between atomic clouds and molecular clouds that basically is determined by the density, or more specifically, the surface density of a cloud. Because as a cloud collapses, the volume density increases, and so does the surface density, grams per square centimeter. And as that increases, the interior of the cloud is shielded from ultraviolet radiation that pervades our galaxy and comes from all the hot stars in the galaxy. And once these clouds become thick enough and shielded enough, you start getting hydrogen molecules. And then the fun really starts, because once you have hydrogen, you start getting many other molecules. And so there's a very rich chemistry operating in the cooler, denser regions of the interstellar medium. And there's a field that focuses on this chemistry that we call astrochemistry. And this is a subject, of course, that has a long history at the Tata Institute, starting with the pioneering work of Vaja and Tarafdar and others, Krishna Swami, and continuing today with the work of Manoj Puravankara and Bhaswati Mukherjee, who work in this field and the sort of related field of molecular astrophysics. In fact, the first conference I ever attended when I was a graduate student at Harvard with Alex Dalgano was a symposium, in fact, the first symposium convened by the International Astronomical Union, the IAU, in Goa, at this spectacular location where the Commonwealth heads of state had stayed. And this was really the first meeting in this subject. And the driving force behind the organization of this was SP Tarafdar, whose work I'll mention briefly later in the talk as well. One point to bring out, and it's brought out in the foreword to the conference proceeding by Vaja and Tarafdar, is that this is truly a multidisciplinary field. And there they note that it combines basic atomic and molecular and grain physics, experimental and observational data, and theoretical calculations and modeling, all of which were the subject of this conference. In fact, the first molecules were discovered in the interstellar medium in the 1920s, but now, 80 years later, more than 190 different molecules have been detected in the interstellar gas or in gas that is flowing out of giant stars. And here is a list from the Cologne database for molecular spectroscopy, showing, ordered by the number of atoms involved, the very rich array of diverse species that have been definitively detected in the interstellar medium. So you'll see there's a variety of very familiar molecules that you could find in your kitchen: sodium chloride, water vapor, carbon dioxide, and so on. And then some complex organic molecules, ethanol, acetic acid, and then some very reactive radicals that, in fact, some of which were discovered first in the interstellar medium and only subsequently synthesized in the laboratory. Almost all of these molecules were discovered by means of radio astronomy, where one can detect the pure rotational transitions of these species with very, very good sensitivity.
So can I again quickly interject? So
Please.
you have shown a beautiful list of all sorts of molecules, some stable, some really transient, I guess. Over a period of time, what is the history of the concentrations of these that you detect? Do people have accounted for these changes? If they have, how and how sensitive?
Yes, so over cosmic timescales, this hasn't been studied so well, and so over billion-year timescales,
Right.
it's a little hard to say. But over shorter timescales, there are changes expected and demonstrated. So as you imagine a transition between a cloud that was puffy and so it was atomic because there was a lot of UV penetrating inside it. If that cloud then collapses and becomes more dense, then there's a time dependence, and people try and model how the chemistry would evolve from the time when the cloud started being dense. And there's people try and use the observed concentrations of these molecules as a chemical clock in the context of a kinetic model for the chemical evolution of a cloud.
Can I ask a quick question here?
Yeah.
Yeah. In your list, I was trying to look for, there are PAH molecules also now detected in many of these interstellar medium, right? PAH, polycyclic aromatic
hydrocarbons. Yes, so that's right. So this list really refers to specific species that have been identified rather than classes of species. So in the case of the PAHs, their presence is very well established through various modes in the infrared. So, for example, the CH stretching mode, bending mode, in and out of the plane of the molecule. But this does not lead to specific, to the identification of a specific polycyclic aromatic hydrocarbon. It could be any one of many different molecules. So for that reason, they're not included in this list.
Okay, thank you.
I should say there are also isotopologues, probably almost equal in number to this, where instead of carbon 12, for example, one might have carbon 13 or oxygen 18 instead of oxygen 16. Okay, so the fact that we see interstellar molecules in such a simple and diffuse physical system, to me, is sort of a dramatic example of how complexity emerges in the universe. So we start with, very simple physics, essentially the Schrödinger equation and the electromagnetic force, and we have a relatively simple system, and we end up with some quite complex molecules. And people have constructed very detailed astrochemical models involving sort of kinetic studies that include many different possible species and many, many reactions. So this is just an example. So I put this up for perhaps a biologist. This looks like the Krebs cycle or something like that. Astrochemistry rests really on three pillars then. We have to understand very well the fundamental physics and spectroscopy of molecules through laboratory astrophysics and related theory. We need to observe astrophysical molecules, either through their emission or if they absorb background radiation. And then we have to conduct or create physical and chemical models of the types of astrophysical objects that we're interested in. And the ultimate goal of this, in my mind, is to obtain thereby information that is of general interest to astrophysicists. And the example that I'm going to focus on today is the density of cosmic rays, which is of broad interest in astrophysics. In recent years, there's been a lot of new instrumentation that has driven the discovery of many new molecules, and particularly instrumentation operating using radio techniques of heterodyne spectroscopy, for example, but at higher frequencies than had been possible previously. So pushing now from millimeter wavelengths into the sub-millimeter region. Now, we live in a planet whose surface is covered 80% by water, which is obviously a good thing on average overall, but it does mean that it's quite hard to observe in the sub-millimeter region from the surface of the Earth because of absorption by mainly water in Earth's atmosphere, water vapor. And there have been several satellite observatories, perhaps the most important of which has been the Herschel Space Observatory, operated by ESA with participation by NASA, which has a particular instrument called HiFi, which has really revolutionized the study of astrophysical gas at these wavelengths. There's also an airborne observatory that I mentioned before, SOFIA, which has a very high resolution spectrometer on it called GREAT, developed by the Max Planck Institute of Radio Astronomy in Bonn and the University of Cologne. And this is a highly modified 747 aircraft with a big hole in the side that has a 2.5 meter telescope. And at altitude, you're above 99% of the water vapor in Earth's atmosphere. And then there are windows in the sub-millimeter region where you can observe from the ground. And you want to go to a very good site. The Atacama Desert in Chile is 18,000 feet above sea level and a very dry desert. And there, a very important telescope, also operated by the Max Planck Institute, is the APEX telescope. And these three facilities have led to many discoveries of new molecules in the more diffuse parts of the interstellar medium. And they're all hydrides, which have very high frequency rotational transitions that cannot be observed typically from the ground, or are very hard to observe from the ground. And I've given a list here of 8 new molecules that have been discovered over the last decade or so. Many of these were discovered by an experiment that is sort of shown on this slide, where if you have a very bright source of radiation at terahertz frequencies, and this might be a region where you have a lot of young stars heating up the interstellar dust, the small submicron particles around them, this can act as a background lamp. And you're not really interested in the lamp itself. What you're interested in is the gas that lies between you and the background source. And you can search for absorption lines that are created by this foreground material. And this gives us a very nice measure of, in fact, the amount of gas that we have.
David, another question.
Yeah.
Quick question. If you go back to 2 slides back for all the, what you said as the hydrides. So yeah, they all look like, electron removed species. That means the OH radical removed with one electron, OH plus. So rather than calling it hydrides, would you just say that oxidized species which are protonated, which are just hydrogen atom?
Yeah, so you could say, well, so there are some neutrals. So there's hydrogen fluoride,
so,
and the mercapto radical.
Correct.
But the other ones are all molecular ions, and so
it's just a it's just a nomenclature that you're using.
Yeah.
Hydride.
Yeah.
Okay.
Right. So I mean, so by hydride, I mean basically a molecule containing one hydrogen element and one or more hydrogen atoms.
Okay. Cool.
So these all have small moments of inertia because of they only have one heavy element.
Cool.
And therefore they all have high frequency transitions. And that's why they had previously been very hard to observe.
Okay.
So let me show you this spectrum that actually I obtained a few months ago at the IRAM 30-meter telescope in Spain. So this is the spectrum of one of these background sources, one we hadn't observed before. And what you see, this is showing you the intensity of the radiation as a function of frequency, but here we've measured frequency as a Doppler shift. So we know the rest wavelength of the molecule we're observing, in this case, HCO plus. And then we interpret all shifts relative to its very well-known rest wavelength as resulting from Doppler shifts from material moving relative to us along the line of sight. So this big peak is emission from HCO plus molecules. So this is protonated carbon monoxide, HCO plus molecules in the source itself. But then you see there are all these little dips in the spectrum at actually longer wavelengths. And here's a blow up of that region. And basically what these are clouds of diffuse gas containing HCO plus that just happen to lie along the line of sight towards this source, but are not associated with this source. So in this picture, basically, you can see this line might intersect many spiral arms in our galaxy that contain a lot of gas clouds. And it's those clouds that we're seeing. And because the galaxy is rotating differentially with an angular speed that isn't constant, but varies with distance, then different clouds will appear with different Doppler shifts in this spectrum. So that's how we detect these molecules in these diffuse gas clouds. So that's as far as I wanted to go with the discussion and introduction to the interstellar medium and interstellar molecules. So I'll now switch gears and go to the second thing I need to explain to you, which is about the cosmic rays. And I'll do this again in an introductory way because I understand, you know, it's an audience with very diverse interests. So I'll make apologies to perhaps the physicists to whom this is very familiar. So the cosmic rays were actually discovered a little over a century ago by Victor Hess, who you see here in a balloon. And he's about to go up, and he actually went up in this balloon with a wicker basket to an altitude of 17,000 feet above the sea level in Austria. Here he is departing from Vienna. And in this balloon, he brought with him an electroscope, which you may remember from high school physics, perhaps, which you can charge up. And when you charge it up, there's a leaf that will be deflected. And as time goes on, that leaf will gradually fall back down when charge is slowly lost from the device. And the reason charge is lost is that the air is very slightly ionized. And so you can really measure the ionization of the air with this simple instrument, essentially consisting of a metal bar with a little gold leaf resting on it. And he took an electroscope up to 17,000 feet to see how the ionization of the air varied with altitude. And the speculation had been that the source of ionization was radioactive rocks in the Earth's crust. And therefore, the expectation was that the ionization rate should go down as you went up, and the electroscope leaf would stay up longer. But in fact, what he found was the opposite. The ionization rate is higher as you go up. And so the conclusion was then that the source of ionization had to be extraterrestrial. And the nature of this source was actually controversial for many years. Here's the front page of the New York Times from 1929. You can see here perhaps there's an article about the Roosevelt transition team as Roosevelt was coming into office. But also on the front page, there's a description of a scientific meeting where there was a very fierce debate between Millikan of the oil drop experiment and his former student, Arthur Holly Compton, about the nature of cosmic rays. And Compton believed they were energetic charged particles. And Millikan thought they were gamma rays. And the whole thing rested a little bit on whether they were deflected by the Earth's magnetic field so that there would be a latitudinal dependence. And Millikan was very dismissive of his former student and referred to his work as less cautious. Well, less cautious or not, this was a case where the student was right and the advisor was wrong. And we now know that these cosmic rays are very energetic, charged particles that are observed over a remarkable range of energy. And here's a spectrum showing the flux of particles as a function of their energy in electron volts. And you can see that they are observed over about 12 orders of magnitude in energy, and obey more or less a power law over that huge energy range. So the most energetic cosmic ray was a single proton with an energy of 50 joules. So that's the kinetic energy of a tennis ball in Roger Federer's second serve. So it's sort of remarkable. Of course, this has then a Lorentz factor, a relativistic Lorentz factor of something like 10 to the 12. And the total density or energy density of these particles in the galaxy is actually larger than that of starlight. So we think of, our galaxy is filled with starlight, but actually there's a slightly larger density of these cosmic rays, about 1 electron volt per cubic centimeter. And these interact with the interstellar gas. The high energy cosmic rays can actually produce an unstable particle called a neutral pion that then decays by gamma rays. And we can observe those gamma rays from the interstellar gas. And lower energy cosmic rays just ionize atoms or molecules in the interstellar gas. And they can also heat the interstellar gas. In fact, they could be the dominant source of heating at the center of the densest clouds. In addition, the electrons that are produced when these atoms or molecules are ionized might have a typical energy of 30 to 40 electron volts. And they can cause additional ionizing and heating. And another important effect that was first recognized by Sheo Prasad and S.P. Tarafdar is that these secondary electrons can also excite electronic states of hydrogen atoms and particularly molecules, exciting the so-called Lymer and Werner bands in the ultraviolet. And so they do give a small amount of ultraviolet radiation at the center of dense clouds, where the starlight is completely shielded by these submicron dust particles. For all these reasons, then, the rate of cosmic ray ionization, and I'll permit myself one sort of jargony abbreviation, CRIR, is a key parameter for our understanding of the interstellar medium. So you could ask what ionization rate is expected. We can measure cosmic rays starting with Victor Hess, but now, of course, we have satellite observatories and spacecraft that can measure cosmic rays. But there's a key problem in relating the density of cosmic rays we measure to what the true density might be far from the sun, for two reasons. First, the ionization rate, which is one of the things we're most interested in for the interstellar gas, is dominated by lower energy cosmic rays than any that we can actually detect. And second, at the location of the Earth, the cosmic rays are excluded, particularly the low density ones, the low energy ones below about 1 giga electron volt in energy. They're excluded by the sun's magnetic field and the solar wind. And you can see that very clearly in this plot here, which compares the spectrum of cosmic rays, the energy spectrum, detected by balloon or satellite observatories in low Earth orbit. So that's at 1 astronomical unit. We astronomers call the radius of Earth's orbit an astronomical unit. So this is at 1 AU. But then there's a spacecraft that has now gotten far from Earth. The Voyager spacecraft, launched in the 1970s, is still communicating with us, and it measures the cosmic ray spectrum. And it's now beyond about 122 astronomical units. It's the furthest human-made object in the universe. It's now entered into probably what is the true interstellar medium beyond the so-called heliopause, where the solar wind is interacting with cosmic rays. So perhaps this is the true spectrum of cosmic rays in the galaxy. But even so, we would have to extrapolate this to lower energy, because the cross-section or the interaction is largest at lower energies. So the scientists associated with the Voyager spacecraft did that extrapolation, and they then estimated that in the interstellar gas, the ionization rate per hydrogen atom should be something like 10 to the minus 17 per second per atom. So the average atom would wait 10 to the 17 seconds before it's ionized by a cosmic ray. But there are many caveats about this. The need for extrapolation to low energy. It's not really clear whether even at the location of Voyager, these effects of the sun's magnetic field in excluding cosmic rays are completely gone. And in any case, this would only tell us the cosmic ray density or cosmic ray ionization state in the local vicinity, and maybe it's different elsewhere in the galaxy. So that brings me to the final part of my talk, which is how we can use observations of interstellar molecules to probe the density of cosmic rays elsewhere in the galaxy. And the way we can do that, as Josh Ishman mentioned, most of the ions that I described to you, most of the new molecules I described are ions, and some of them are only produced as a result of a network of chemical reactions that is initiated when a cosmic ray ionizes a hydrogen atom or a hydrogen molecule. And so the idea is that then by measuring the concentration of those ions, we might be able then, in the context of a model, to determine the cosmic ray ionization rate. So what result do we get? Well, the answer is it depends. It depends on what kind of interstellar gas cloud we're looking at. And there are several types of interstellar gas cloud in the neutral interstellar medium. So these are all clouds between about 10 and 100 degrees Kelvin. But if you start with a very low density cloud, you'll have mainly atoms, and that's called a diffuse atomic cloud. Then as the cloud gets a little bit larger, there'll be some shielding of the ultraviolet radiation that will allow the fraction of gas that is molecular to get up to a few percent. And then there's an intermediate case. And then finally, you have a dense molecular cloud, which is so thick that there's essentially no ultraviolet starlight at the center of the cloud that might destroy molecules. And a key measure of this sequence is what astronomers call the visual extinction. It basically tells you how much the light has been extinguished as one moves from the surface of the cloud to the center. And the way it's set up, it's a linear measure of the surface density. So if we look at the densest clouds and infer the cosmic ray ionization rate based on observations, again, of HCO plus, as the molecule I had discussed earlier, the result seems to be in perfect agreement with what the Voyager scientists, Cummings et al., inferred it would be based on observations of actual cosmic rays near the sun. There's another method of doing this involving water vapor in dense molecular cloud cores where there are no stars. And so the only UV field is these Prasad-Tarafdar photons created by cosmic rays exciting hydrogen molecules. And that UV can photodesorb the water that is frozen out onto the surface of grains and put it in the gas phase where it can be detected. And that gives a very similar answer. So it looked like everything was in perfect agreement until people started probing these diffuse molecular clouds. And the result they got there was very much larger. So in diffuse molecular clouds, one can observe in absorption the H3 plus ion. So it's a protonated H2 molecule, if you like. This was actually discovered by J.J. Thomson, the discoverer of the electron in the early 20th century. And the spectroscopy was elucidated by Oka at Chicago, and that allowed it to be actually discovered in the interstellar gas. And this acts as a very good probe of the cosmic ray ionization rate, because cosmic rays ionize H2 to form the H2 plus molecular ion. And then that will transfer a proton to another hydrogen atom to form H3 plus.
David, I think there's a question. Prasoon,
Yeah.
can you unmute and ask the question, please?
Yes, yes.
Yeah.
So you can.
Yeah, David, I just had a question, which is that do you assume that these clouds are in thermal equilibrium? Because otherwise, probably the numbers will be different, right?
In thermally, well, they're not in thermodynamic equilibrium, but they are at a particular temperature and thermal equilibrium in the sense the molecules have a Maxwell-Boltzmann distribution. And we also assume that they're in steady state so that these abundances have reached an equilibrium where the rate of formation of any molecule is equal to the rate of destruction. I don't know if that, does that answer your question?
Yeah, so just the follow-up thing was that would that be same for different types of clouds, like the one diffused and the previous thing that we discussed?
Yeah, so the result would depend, the amount of H3 plus you get would depend on various physical parameters because there's several reactions involved. So one needs a fairly detailed model and one needs to know the reaction rates very well. And one key question was the rate at which this H3 plus would be destroyed by reactions with electrons, which was measured in the lab by Ben McCall, and who was a student of Oka's. And so by means of these detailed calculations, they inferred that the ionization rate was in fact about an order of magnitude larger than what it had been inferred to be in the dense molecular clouds. So this perhaps is providing evidence then that the sun is atypical. We have a lower cosmic ray.
David, can I? There is a question on YouTube. Question from YouTube. So
okay.
The question is, I'll read it out to you. What is the range of UV photon energy available in the interstellar medium?
Right. So we basically have UV photons over a wide range, but then truncated at an energy of 13.6 electron volts, which some of you will recognize as the ionization potential of hydrogen. So at energies above that, and it corresponds to a wavelength of 912 angstrom, there's a huge opacity due to photoelectric absorption by hydrogen atoms. So basically the spectrum cuts off sharply beyond 13.6 electron volts. And that's actually a very important feature that determines the chemistry. The point then was that in these diffuse clouds, it looks like the ionization rate is much higher than in the dense clouds. And we've studied this in a little more detail by using more elaborate chemical models that had been used, but the same data on H3+. And what we're finding now is marginal evidence for the idea that within this class of clouds where we see H3+, there is a decline in the cosmic ray ionization rate with cloud size. And you can see that in this plot where we show the inferred cosmic ray ionization rate as a function of two measures of the cloud size. One is the surface density of hydrogen molecules in particles per square centimeter, and the other is this visual extinction, which refers to the amount by which starlight is extinguished. And there's sort of a 3 sigma detection of a decline here. And if you continued this slope, it would actually take you then in the diffuse clouds to a value that was about an order of magnitude lower. So this seems broadly consistent then with the idea that the cosmic rays are shielded from the center of clouds, and this can be understood theoretically. So this slide then shows our best estimate of the cosmic ray ionization rate for clouds observed with H3+, the diffuse clouds, compared to the value for the dense clouds.
Quick question
Yeah.
from the Zoom audience. So there is Atanu Kole who is asking, when there is a supernova explosion, shock will be generated. In that region, how then the pressure equilibrium is valid?
No, so that's exactly right. When a supernova explodes, it will send shocks traveling through the interstellar medium, and there'll be a large overpressure in those shocks. And that can persist for tens of thousands of years. And we see these shocks lighting up what are called the supernova remnants, which are not really material that was ejected by the supernova, except in the very earliest phases, but is a region of higher pressure gas that has been compressed by a shock. So these different phases are in rough pressure equilibrium, but not perfect pressure equilibrium because of supernovae. And also if a star is formed and heats up the gas, the temperature will quickly rise by 2 orders of magnitude, but it'll take a while for the gas to expand. And so you can have an overpressure in that case as well. Well, I'm running a little behind my schedule, so I could skip the final thing that I wanted to discuss and go to conclusions, or I could take another few minutes to describe that, and it's up to you. I'm sorry I've been going. You
can actually take the 5 minutes and finish if you want.
Okay. Yeah. Then I'll do that. So basically, the final point I wanted to make is that one can look at even more diffuse clouds by looking at certain molecular ions. that are produced by reactions initiated by cosmic rays. And those include OH plus and H2O plus, which we have detected in absorption with the Herschel Space Observatory in this experiment I described, where we're looking at background sources and looking for OH and H2O plus in the foreground gas. And we're actually going to extend this next year with a large program called HyGal, the HY is for hydrides, where we'll use SOFIA to make additional observations of these molecules. And we've interpreted them, and I should have mentioned my close collaborator, Mark Wolfire, who has been modeling the chemistry in these clouds. We've used detailed diffuse cloud models, rather similar to those in the pioneering work of Thielens and Hollenbach 30 years ago, and done an extensive parameter study that allows us to infer from observable quantities what the cosmic ray ionization rate is. So in this plot, you see two observable quantities, the OH plus to H2O plus abundance ratio and the OH abundance relative to hydrogen atoms. And in this plane of observables, you'll see contours of model predictions. The red contours are models with a given thickness of the cloud measured in this visual extinctions parameter I mentioned. And the blue curves are contours of constant cosmic ray ionization rate. And the black points are the data observed towards many, many background sources, and we'll expand this with HyGal. And so that allows us to infer a cosmic ray ionization rate. Amazingly, there's another molecule that we can also observe. It's argonium. It was discovered with Herschel less than a decade ago. So it's protonated argon. It is a molecule that is found in the most diffuse clouds because it's destroyed rapidly in reactions with H2. Argon actually has a lower proton affinity than H2, and so it's destroyed by H2, or so argon H plus is destroyed by H2. So combining all these constraints, we were able to derive this number for the cosmic ray ionization rate in the diffuse atomic clouds. And it's essentially identical to what we get from H3 plus. And it also doesn't vary that much from one cloud to another, suggesting then that the cosmic ray ionization rate and the density of low energy cosmic rays is quite uniform within the galaxy, which is perhaps at odds.
David, there's a question. Yeah. Mike, why don't you go ahead and ask?
Hi, David. So my question is like, when we search, like, for example, you said this discovery of argon H. So did you a priori know that this molecule existed, or was it like a chance discovery? And if it's a chance discovery, how do you go about identifying the molecular species?
Right. Okay. So I can certainly digress to that. So it was actually just this unidentified spectral line that we saw all over the place in the interstellar gas. So we had this line, we knew its frequency, but we really, and we had some very good spectroscopists on our team, and we couldn't figure out what it was. Now, people make catalogs of spectral lines for various molecules. And so you can look in those catalogs, and we found nothing. In fact, one of the catalogs was maintained by one of the members of our team. And then...
JD, can I just comment on this question? This is Sanjay. This ARH plus was reported by Hannah Reisler in 1989 at USC, I think. So it is a laboratory identified molecule.
Yes, right. So yeah, sorry, I should have said that at the beginning. So yes, it has been very well, it was identified, as you said, a while ago, and there's very good spectroscopy on it. So we know the rest frequency to much better accuracy than we need to know it. And so it should have been in these catalogs, but we couldn't figure out what it was. And then there was a talk given at a meeting by Mike Barlow, and he and his collaborators had detected a line at exactly twice the frequency, almost exactly, in emission actually from the Crab Nebula, a young supernova remnant. And they also detected this line. So this basically tells you, this harmonic ratio 2:1 tells you it's a simple molecule with a singlet sigma ground state. And they also said they identified it as being argonium. And we were just stunned by this. We went back to the catalogs, and there's two issues actually. First, there was a note in the catalog that prior to about 6 months before this was announced, they had miscatalogued the frequencies and put in the frequencies for the first excited vibrational state. The other thing is, if you ask any chemist what the atomic weight of argon is, what will they say? Somebody? It's 40. But it turns out that in the sun, argon has 3 stable isotopes, 36, 38, and 40 argon. And 36 argon is by far the most abundant in the astronomical universe. And this is what was detected here. But in the context of the Earth, in fact, our atmosphere, which is maybe 1% argon, comes almost entirely from the decay of radioactive potassium-40 in the crust. And so it's a very unusual case where, a chemist will be thinking of the different isotope than what is actually present in the interstellar medium. So in fact, we detected 36 argon H+, and then we followed it up. We actually got 38 argon H+. But 40 argon is very low in abundance, so we never saw that one.
Okay.
So it was sort of an amazing story of how this had escaped detection and was eventually identified. So this then gives us another point in this plot. And so basically then the picture emerging is that there's a certain density of low energy cosmic rays that doesn't vary much in the galaxy, is roughly 2 × 10⁻16 per second. As you go into dense molecular clouds, the rate seems to diminish, and this can be understood by models for how cosmic rays would be propagate through clouds and be shielded from the interior. And for reasons that still remain a puzzle, this higher number, which should apply in the solar system, does not seem to be consistent with actual direct measurements of cosmic rays. So perhaps the Voyager spacecraft is not yet completely free from the effects of solar modulation, or perhaps despite the fact that there isn't much variability, perhaps the sun is located in a region where the cosmic ray ionization rate happens to be somewhat lower. So I'm sorry I've gone over here. I hadn't quite anticipated so many questions during the talk. So I'll just put up my summary and be happy to take further questions if you want to continue this.
Yeah. Yeah. So you can do the summary. Yeah.
Okay. So I mean, basically, the points I've tried to convey are that molecules are ubiquitous. We see them in many, many different astrophysical environments, that our galaxy is filled with a diffuse interstellar medium, and that cosmic rays fill our galaxy with an energy density that is comparable to that of starlight. and then sort of combining these two threads, that observations of interstellar molecular ions allow us to measure the density of low energy cosmic rays remotely. And the low energy cosmic rays do appear to be excluded from larger gas clouds by the shielding effect of the surface layers. And rather puzzlingly, the cosmic ray density or ionization rate inferred based on the cosmic ray spectrum appears anomalously low in the vicinity of the sun, which is of course the only place where we'll be able to make direct measurements of cosmic rays rather than just infer them from molecular ions. But somehow the agreement between these two numbers, which are sort of using, similar methods, but entirely independent methods, is sort of encouraging to me that, our understanding of the chemistry is really good enough to say that this difference is real. So that's my summary. Thank you.
Thank you very much, David. That was a fantastic colloquium. And just wanted to thank you again for doing it at your very early hours of the morning. I have some questions that I had not taken up during the colloquium. There is a question by Shujit Kumar Das. And there are some people who are raising hands. So I'll just take the first question from Shujit Kumar Das. He has written, I want to know that during transformation from atomic to molecular cloud, how a greater surface density reduces UV radiation field at the cloud center and permitting formation of molecules.
Right. So if I have ultraviolet radiation traveling through a cloud, it will be absorbed particularly by these dust particles, which are well mixed with the gas. And so the amount of absorption I get will depend really on the surface density of the cloud, not the volume density. It's really the integral of the number of those dust grains per unit volume integrated with distance along the line of sight.
Okay.
So if I have a fixed amount of material, but I make my cloud smaller, then the surface density will be higher, and the effects of the dust absorption will be greater.
Okay.
There's another point that is important, particularly for molecular hydrogen, which is that the photodissociation of molecular hydrogen by UV radiation, and this occurs between about this cutoff of 912 angstroms and about 1150 angstroms. That process follows the absorption of UV photons by H2 in lines, in spectral lines. These are the so-called Lyman and Werner bands, so electronic transitions, but there's no continuum photodissociation that can be measured.
Okay.
So what this means is that hydrogen molecules are very effective in shielding deeper in molecules from exactly the radiation that could dissociate it. So astronomers call this self-shielding. Yeah. And it basically means that even without the dust absorption, you can get a significant transition from atomic to molecular hydrogen, where you get a small amount of molecular hydrogen in the outer parts, and that shields the more interior parts from exactly the UV wavelengths capable of dissociating it.
Okay.
So those are sort of the two reasons.
Fascinating. Okay. I would like to now invite Gargi, who has raised up her hand.
Hi. I have a question that when you determine the cosmic ray ionization rate using the H3+, you need to know the density of electron. So how you determine it?
Right. So that's a very key point. We do need to know the density of electrons. And so we have to have a model for these clouds and how the density of electrons varies as it might with depth inside the cloud. So it is somewhat model dependent.
Yeah, so
but in fact, to quite a good approximation, most of the electrons come from the element that is most abundant and that can be ionized by the UV field that is left beyond 912 angstroms. And that element is carbon. So the abundance of electrons is, under many conditions, very close to the abundance of carbon, or carbon plus, which is basically then just the elemental abundance of carbon. In other words, most carbon atoms are singly ionized in the interstellar gas that we're looking at. And so you get a number of electrons equal to the number of carbon atoms.
So do you include pHs in your model? Because
yes,
that affects.
we do. Yes, so PAHs indeed can assist the recombination of the gas because they provide a nice surface area. So that is included, the recombination that occurs on PAHs. It's a good point.
Okay. Okay, now I have Lokesh Trivedi.
Yeah, just a quick question. Is there an understanding of formation mechanism of C60 fullerene? What you see, C60, C70, is there a understanding of the mechanism?
That is a very interesting question. So yes, as you know, these molecules, C60, C60 plus, C70, C60 is the soccer ball with 60 entirely equivalent carbon atoms, have been observed in the interstellar gas. It's an amazing story. And the origin of these is not that well understood. It's possible. So I guess the two things are, is it made by a bottom-up process where you start with smaller molecules and somehow form C60? Or could it be a top-down process where you start with some kind of carbonaceous grain, and we believe there is graphite in the interstellar dust grains, and could, the fragmentation of that be the source of the C60? It's not a field I'm that familiar with, but I think it's really still considered an open puzzle.
Okay.
Okay, yeah, thank you. And just wanted to comment that I think it's a very wonderfully organized colloquium. Thank you for this.
Oh, thank you very much.
Thank you. There is a, Manoj, there is a question on YouTube. Do I need to read it for you, or you can do it?
There are a few questions in the Zoom. I thought we'll finish those.
Okay, okay, fine. So, so there is a question from M.R. I don't know who this is. Is it possible to get molecule in more diffuse environment, such as in the case of 10 to the power minus 3 per centimeter cube, 10 to the power minus 3 per volume unit centimeter cube? Yeah.
Yeah. So that's very doubtful that you could, and part of the reason for my answer is that this very diffuse gas is also very hot. I mean, basically it's gas that was heated up to 1 million Kelvin by supernovae and then expanded until its density became that low. And so I think the answer is no, that really the most diffuse clouds in which we can observe molecules probably have a density of something like 30 particles per cubic millimeter.
Okay, well, thank you. Jibok Mukherjee is asking, what are the effects of absorption of 10 to the power 21 EV cosmic particle by the ISM?
These are just very, very rare cosmic rays. Their effect on the interstellar gas is minimal, yeah, I'm not quite sure what happens when such an energetic particle would collide with a proton. Probably all sorts of interesting particle physics things would happen that's sort of outside of my area of expertise.
Okay.
But if we go back to this figure with the flux of cosmic rays, it's a very steep power law. Let me just go to that. So yes, I said there are 12 orders of magnitude in flux, in energy, but this corresponds to 30 orders of magnitude in flux. So, you know, all the interesting effects, or the effects that determine the nature of the interstellar medium, are dominated by the lower energy cosmic rays that have a much larger flux.
Okay. There is a question from Samarjeet Singh. Which astrophysical molecules in your list cannot be synthesized on Earth?
Well, I think the answer is none, and that's because there's really no way of reliably enough predicting the spectroscopy that without actually taking a lab spectrum. So, you know, theorists can predict spectra, but the accuracy is really not adequate to make an unequivocal identification of a molecule without actually having a spectrum in the lab. And so basically, by definition, obviously, any molecule for which you can take a lab spectrum, you have to be able to synthesize. Now, there were some cases, and one example was the C3H2 molecule, which is has linear, but also a cyclic form. And that appeared as an unidentified spectral line, radio wavelengths. And it was only subsequently synthesized in the lab of Thaddeus and now McCarthy. Maybe it was already McCarthy's lab, I can't remember. Anyway, the lab at Harvard. And basically, in response to the detection of an unidentified line, it was then synthesized, and then they could demonstrate that it had the right frequency. So I think that's the answer to that question.
Okay.
Jyotishman, can I just tell people that David has kindly agreed to stay back for some more time for more extended discussion if anybody wants to have with him. So yeah, just wanted to.
Sure. And then the last question from Sanjay. I think Sanjay can ask on the video screen. Why was HCO plus emissive?
Yeah, David, in your first part of the talk, you had the huge emission from HCO plus, while the rest of them were in absorption.
Right.
So where does the HCO plus become emissive? Why does it become emissive?
Yes, so the reason it becomes emissive is basically this cloud has a reasonably high density by our standards, say 10 to the 3 or 10 to the 4 particles per cubic centimeter. And so inelastic collisions between HCO plus and H2, for example, can excite the lowest few rotational states and then can decay. So it's basically collisional excitation followed by spontaneous radiative decay.
JD, if I can ask one more question.
But I couldn't hear you.
Are you able to hear me now?
Yes, now I do.
Yeah, there's one more question. Maybe it's just semantics. Why do you term these various rates that you found cosmic ray ionization rate? Actually, these are the chemical reaction rates, bimolecular chemical reaction rates between H plus and various species. What you need to find out is the cosmic ray density, I think. So why this nomenclature of cosmic ray ionization rate?
Okay, so many of the reactions are bimolecular reactions. In fact, most of them are. But okay, yeah. So in a way, this is a bimolecular reaction in that it involves a cosmic ray and a hydrogen atom.
Correct.
But just the way that traditionally this is characterized, we treat this as just the rate per atom. But you're right, it's basically has to do, well, it would be the density of cosmic rays times the speed times the cross section, basically. That would be the rate per hydrogen atom.
Right. So basically just the, depending on the cosmic ray density and the hydrogen atom density, you would have certain population of H plus, and you're assuming that population of H plus to derive the further kinetics of the observed species, right? And from that you get the rate constant for the given reaction. So what you're inferring is the cosmic ray density, I suppose.
Yes, exactly. And I hope I made that clear. So yeah, we're not talking about a rate constant. We're basically talking about a rate per hydrogen atom. And if we know the rate constant, which we think we do very well, then we're really measuring the density of cosmic rays.
Okay, thank you.
Okay, thank you, David.
Yeah.
Okay, so there is one question from YouTube, Manoj.
Yeah, I can. Yeah, David, I'll read the question out to you. I think it's what's the frequency and bandwidth of absorption line observations done using ERAM 30-meter telescope observed on June 2020. I think it's about that H3CO plus, HCO plus.
Sorry, what is the frequency bandwidth?
Frequency and bandwidth of the absorption line observations.
Okay, yes. So the frequency is, can't remember the exact number, but it's around a little less than 100 gigahertz. And the simultaneous bandwidth covered is 8 gigahertz. So these better receivers now start to have quite a large bandwidth. And actually it covered several other molecules that I didn't discuss, but we, in the same spectra, we detect CS, HCN, HNC, HOC+, all of these molecules we detected in absorption at the same time. The HCO+ is the strongest, but there are many others.
Okay. Okay. So Manoj and everyone, I would like to thank David once again for this wonderful colloquium right from his home, very early in the morning. I think it's 7:30 or 6:30 in the morning.
Right. So it started at 6:30 and now it's almost 8. The sun has risen.
Okay. So of course you will continue with the interaction. I just need to formally close and thank you as well as the audience for joining in today, as well as especially the technical support in the institute that ensures that all, apart from these individual connections that everybody makes, there is always a connection available for audience to join in through the lecture theater. So I would like to thank Mistry ji and the lecture theater for arranging that, Mr. Rajesh Mistry. And also I would like to sort of remind all of you that we continue next week on the 30th of September with a chemist speaking to us from JNC ASR Bangalore, Professor Kanishka Biswas, and he's going to talk about crystalline solids with intrinsically low lattice thermal conductivity for thermoelectric energy conversion. So with that, I formally conclude this session, and I would like to thank David once again and all of you. Please carry on with the conversations that you really want to have with David. And David, on a personal note, thank you for doing this. And I hope to again maybe get in touch with you later. Okay?
Great. Well, thank you very much. This was a real pleasure for me as well.
Thank you.
Okay, people. So we will. So please stay on if you want to have a more detailed discussion with David. He has kindly agreed to stay online for some more time. So Jyotishman will be leaving, but we could continue.
Yeah, sure.
Bye-bye.
Bye-bye.
Bye-bye. Thank you.
Yeah, people who want to have discussion can stay on, and David will be here for some more time. So David, there was one question on Zoom, which is basically, are there any young supernova remnants near to the lines of sight where you see high cosmic ray density?
Yes, that's a very good point, and I should have mentioned that there is one case that is not in our sample, but others have observed, particularly Nick Indriolo, where a cosmic ray, an enhanced cosmic ray ionization rate is inferred in a cloud that is close to a supernova remnant. And of course, you know, the context for this is that supernova remnants are believed to be the most probable site for the acceleration of cosmic rays by, you know, the process first elucidated by Fermi, where you can sort of get magnetic mirrors that are converging on either side of a shock front. And so the cosmic rays can be trapped, if you like, between these converging mirrors and greatly accelerated. Every time they bounce between the mirrors, they acquire a velocity boost. Yeah, that's something I should have mentioned.
Yeah, this was a question from Prasoon Datta. I think he has a follow-up. Prasoon Datta, please go ahead and ask your follow-up question.
Yeah. Hi, David. So in the same note, so if you have these diffuse clouds, so it may be that at different, if you approach the center or the denser part of the diffuse cloud from different directions, you will see variation in the density from which direction you approach. Is that a possible observation? Because
you're saying
maybe
if we had a diffuse cloud close to a supernova remnant, could we determine the direction at which the cosmic rays were coming in? Did I understand that correctly?
yes, or the density is higher in the direction of the supernova remnants in general.
Yeah, so that would be interesting. I don't think there's any case where one can do that that we know about yet. In fact, yeah, well, it's an interesting idea. Whether, I mean, so far we can't, all we can really do is determine the average cosmic ray ionization rate within a cloud. We can't say that, you know, one side of the cloud is more ionized than the other, but
that's a resolution issue, I guess.
yeah, it's a resolution issue. Yeah, exactly. And we need a background source, and it's really the density of background sources. So basically, there's typically, you know, only one background source behind any given cloud, or zero. So it's not possible to resolve. Although in this HiGAL program, we do have a few sources that are close together. So, I mean, a few background sources against which we observe absorption. So it might be possible to find small scale variations in the cosmic ray ionization rate, which would be very interesting.
Maybe towards the bar, or I mean, I understand that the velocity difference will be very less, but still.
Sorry, towards the
central bar of the galaxy.
Yes, if we don't actually have any sources that far away, unfortunately, in HiGAL. But, you know, with future experiments, it's possible that one could start to do these very sophisticated studies. Yeah.
My interest was because that will also kind of trace how the pressure equilibrium establishes as the, I mean, the kind of the modern pressure equilibrium Mackey-Ostraker theories. How does the cosmic ray penetrate within these molecular clouds?
Right. So at the moment, we can only probe this just by looking at a sample of successively larger clouds and see how the H3 plus abundance varies.
Yeah. Thank you. So that was.
Okay. Thank you, Prasoon, for your questions. We have another question from Mayank. Please go ahead.
Yeah, Professor David. So if you look at the absorption feature on the bottom panel, you see around 50 kilometers there. It's like a double hump feature. So is this a real feature, or if it's a real feature, what is it telling us?
Yeah, so it's telling us it is real. This molecule has no detectable splittings. So it's really telling us there are two clouds separated only by a little bit in velocity.
Do we have any position information, like either in redshift, or since these are local, so since uh, do we have any idea about the distance difference between the two?
No, we probably don't. Yeah, it's probably, I mean, one could, try to estimate distances knowing the rotation curve of the galaxy, exactly how it's differentially rotating. But at this scale of difference, I suspect, you would be dominated perhaps by random motions, which would make it rather hard to infer a distance based purely on the velocity at an accuracy that would be sufficient. But that's sort of one thing we have to do, is sort of figure out now what our best estimate is for the distance of all these many clouds that make up this absorption spectrum. I should say the reason we got this was that this is one of the sources that we'll be observing with Herschel. I'm sorry, with Sophia. And so we'll get many, many different molecules in these different clouds and be able to infer the, among other things, the cosmic ray ionization rate in each of them.
Any other questions, comments? Feel free to interact with David. So,
David, this is Vaibhav here. I have a question. There are, I mean, the molecular species that you have shown, there are a couple of negative ions.
Yes, yes.
So are these the colder regions, or are they from a less dense region?
No, they're generally from cold, dense regions, and also from the circumstellar envelopes of giant stars. So that was a very big surprise, the discovery of these anions. And it's actually a mystery as to why they're as abundant as they are. So there've been various theories that propose, because one sees the neutrals as well, I think. And so there are various theories that propose the process of radiative attachment, where these neutrals can acquire an electron, and radiative meaning that a photon is emitted. And the rates for that radiative attachment, to get this to work, had to be assumed to be, I think, unreasonably high. So it's a bit of a mystery why you have these anions. It's a very interesting subject that I haven't worked on myself.
But there can be other possibility of dipolar dissociation of a bigger molecule.
Yeah, so I'm not sure that's been looked at, but that would be interesting.
Because that has a much higher cross-section, and if you have energetic particles, that should in principle break a big molecule and give you negative ions. And of course there has to be corresponding positive ion also present around, but
right,
that should not be a problem in principle.
So you say, right, and that would be a non-radiative process, so it could be rapid. So you're saying you could dissociate, for example, HC5N, which is a known molecule, I think. And yes, it is, it's up here. So perhaps you could dissociate that into a proton and C5N minus.
Yes, yes.
Would that be a photodissociation or some other kind?
No, so for example, energetic electrons or energetic charged particle can also cause this dissociation.
I see.
And this is a very well-known phenomenon that is available for energies above ionization potential of the molecule.
I see.
Yeah.
Okay, so that's a very interesting thought. I haven't actually worked on this myself, and I don't know if other people have already considered the process that you're talking about or not. But yeah, that sounds very interesting.
Another question I have is, you talked about isotopologues of all these species which are also present in good enough number. Do they also show proportionality to what isotope abundances that we actually look around? Or do they show different ratios?
Yes, so that's another very interesting question. The particularly when we're talking about deuterium, there can be, and it's often the case that molecules containing a hydrogen substituted for by deuterium are much more abundant than the cosmic ratio of deuterium to hydrogen nuclei, which is only about 10 to the minus 5. So for example, if you look at methanol, they see deuterated methanol that might be 10% of ordinary methanol. And in fact, they see doubly deuterated methanol and even triply deuterated methanol, which, you know, if you were just putting in the deuterium randomly with an abundance of 10 to the minus 5, to have triply deuterated methanol, it would be a probability of 10 to the minus 15, and you'd never see it. So this astronomers call fractionation. And in the case of deuterium, it's quite well understood as being a result of the different 0-point energy. So if you have a deuterated species, it will have a lower 0-point energy, with half a quantum of vibrational excitation that you always have. And so that will be energetically preferred, particularly at lower temperature. So that's sort of one way that you can get an isotopic enhancement, particularly in the case of deuterium. But it's also been observed for carbon-12 and carbon-13. And then the other effect, in addition to this 0-point energy effect, is that you remember how I talked about the self-shielding. So molecular hydrogen can shield itself, but its UV transitions are slightly shifted from HD. So that means that HD won't be self-shielded by, or won't be shielded by H2. And since its abundance is lower, its self-shielding effect will be different. So there are two things that do lead to this fractionation effect, where the isotopologue abundance does not reflect the isotopic abundance. So it's the different 0-point energy at low temperature and possibly differential self-shielding.
But different 0-point energy makes a lot of sense for H and D, but I don't know how much effect will it have for the heavier.
Right, so it's a much smaller effect.
Yeah.
And the big effects are only observed for D and H.
Yeah. Yeah.
And I think the effects for, say, carbon-12 and carbon-13 are much more minor and arise from the different self-shielding.
I see. Okay. Thank you.
And I don't believe there are any well-established cases for any other elements.
I see.
So actually what one often does is just turn this around, and it gives you a nice way of measuring isotopic ratios. So if you just want to look at electronic transitions of atoms, of course, the shifts are very small, yeah, and often undetectable. But if you look at rotational transitions, the shifts are just go as a reduced mass. So that's a big effect. So the rotational lines in the radio are hugely shifted. So people observe isotopologue molecules and now assume that for the heavier elements there's probably rather little fractionation. and use them to derive isotopic ratios in different environments. And that can be very useful because the different isotopes are made by different types of nuclear processes. So, you know, a low mass star might produce certain isotopes, and supernova might produce others. So if you can measure these isotopic ratios, you can maybe get an idea of the history of, you know, that region of the galaxy in terms of the relative numbers of low and high mass stars that have formed in the past.
Yeah. So actually, that is something which I was going to ask, is that it is not just the presence of different isotopologues and their different ratios not only reflects upon the destruction mechanism, but also on the formation, and that should give us idea about the nuclear reactions, for example, that are resulting in different isotopes appearances in the molecular or not molecular but the interstellar clouds, which are eventually resulting into these isotopologues.
Exactly.
But this also give us the information about, you know, the not just the composition but also the age of the material which is over there and the evolution, and is there a possibility of any seeing any nuclear spectroscopic signals that might also match with this isotopic abundance, or show what kind of nuclear reactions that are happening at that
Yes. So, you know, I'll give an example of things that people think you might be able to do. If you could go to very high redshift, and this hasn't really been done, I think, very well yet, but if you could look at very high redshift, you could maybe hope to see, you know, the effects of isotopic ratios that are different, say, in supernovae than in lower mass stars, because, let me think about this. Yes, here's one of the arguments, that certain elements are made in the late time evolution of low mass stars. And so it might take a long time to produce that element or that particular isotope because, you know, you have to have a low mass star and it has to exhaust its nuclear fuel at the core and become an evolved star, a giant star, where these elements are made. So there's some hope, you know, maybe you would see the signature of that if you could look at a time in the universe at a high redshift where there hadn't been enough time yet for, say, a 2 solar mass star to leave the main sequence. But I don't think that's been really unequivocally established in any case that I know of. But it's the kind of thing one might hope to do indeed.
Okay. Yeah, thank you.
Are there other questions, comments? David, if you're really tired, we could stop in the next few minutes if you want.
Sure. It's, I'm happy to stay if there are, you know, still people who want to chat.
Okay.
Or, yeah.
Okay.
Whenever.
So please go ahead if you have questions, or, you know, if you just want to interact. We can have it for a few more minutes.
David, while people are thinking about questions,
yeah.
I would say that I am surprised that you are not asked any questions on phosphine.
Yes, I was too.
You made it sound sufficiently different from detection of molecules in planets.
Yeah, no, I was thinking about what I could say diplomatically about the phosphine thing. So,
yeah.
Yeah. I mean, if you actually look at their paper,
yeah,
you you know, they specifically say this is not a robust indicator of life.
Right, right. Yeah.
But somehow, I don't know, the press seems to have picked this up in a way that, you know, seems to go way beyond what is actually said in the paper. So
No, but although David, in the RIS press conference, Sarah Sager made it a point to say that phosphine is produced by life on Earth, and
yeah.
Yeah.
Okay, so maybe the press isn't so much to blame. Anyway, to me, yeah, I'm sort of reminded of this, you know, famous dictum that I think is attributed to Carl Sagan, that, you know, extraordinary
Right.
claims require extraordinary proof, and just saying, you know,
Yes.
we don't know how else it would be made seems a
Right.
valid argument to me.
So people are talking about, you know, this is a detection of a single line from a species. So maybe the first step is to detect another line transition, perhaps in the infrared. I don't know.
Yeah, so that's another point. I mean, that to me depends, and I don't know, it sort of depends on the density of lines that you have, right? I mean, we all believe in atomic hydrogen, and that's a single line detection at 21 centimeter. It's just that
Yes.
there are no, you know, the density of lines in that spectral region is minuscule. So the chance that something would agree to within the precision with H1 and not be H1 is essentially zero. I don't know enough about the Venusian spectrum to know whether that's a concern or not.
So that would be a concern related to the contamination. But what about the abundance determination? So, because sometimes that is helped, like when you have multiple lines, and particularly it's not really a foreground thing. So you need to know the structure of Venus very well. Like
Yeah, so
the
you'd have to model the
model,
excitation.
it is model dependent. So
Yeah. But on the other hand, they're sort of saying the chemical models fail by, I can't remember, maybe a factor of 1 million. So,
yeah.
But, you know, well, I've had a similar thing. We detected water around a carbon-rich AGB star with SWAS. And our theory for this was that, you know, it's very hard to understand why you would get water in a carbon-rich environment, because all the oxygen would be in the form of CO, and there'd be very little left over to form water. So our model for this was that this AGB star had vaporized objects in a Kuiper belt around the star, and that would dump water vapor into the gas phase and would explain why we see water. So, you know, that was the model we had, and there are various predictions that could only be tested with Herschel. But anyway, we put that out, and actually we had a press conference on that as well. Now, I would say, you know, that's not an extraordinary claim in the way that this is. In fact, this will happen when the sun becomes a red giant. You know, Pluto will be vaporized, and so, and the icy moons of Jupiter and Saturn and so on. So maybe it's not such an extraordinary claim, but anyway, and we, you know, in our defense, we also made a specific prediction with Herschel that certain avalines should be relatively weak because all the water would now be fairly far from the star, and there would be very little in the inner envelope. Well, Herschel came along, and we and others found there's lots of warm water there, so it must be coming out of the star, and this theory then is wrong. So, and I would say it's still not understood why there is water in these carbon-rich envelopes. I mean, there's a couple of proposals, neither of which seem that plausible. So it just remains a mystery. But, you know, the interesting explanation we had can be ruled out. And so there must be something going on in the chemistry that we just don't understand. So.
Yeah. More questions, comments? Basudhi, do you have anything more?
No, it's fine.
Okay, then I think we should
Yeah, I think it's been a long,
yeah,
it's been a really long haul
David.
for David.
So David, before you go, I need to formally close this. So Jyotishman has asked me to say a few words. So let me just do this officially, close the session.
Okay.
So David, I'll again like to thank you for this wonderful colloquium, and to all of you listening to us on YouTube. Please watch our official YouTube channel, TIFA Platinum Jubilee events, for more such events. All right. So let's close now.
Thank you, David.
Oh, great. Thanks. Sorry, it went on a little longer than.
No, I think it's perfectly all right. Like, I think it's
okay.
fine.
So it just more during that I was used to. So
yeah.
Okay.
Yep.
Great.
Bye.
Nice
Bye.
seeing you. Yeah.
Bye, everyone.
Stay safe. Bye bye.
Thank you, David.